This is Bill Foote, and we're going to talk about deviances today. But before I get to that, I wanted to show you something here. Let's see if I can bring this up. A picture that I promised in another video. This is the plot between Pareto smooth importance sampling score, low to high, and that's not working for me, and reliability, the shape parameter of a generalized Pareto distribution. Very clever trick used by Aki Ventari and Atari, rather, and Gilman and others to ferret out what appears to be a very large drain on the information of an entire set of data. And again, this is leave one out. So we can look at these different observations of the ones left out, their likelihood when left out, leave it out, and some notion of where they plot in terms of reliability. And we're going to use this idea in exactly what follows. And before we get there, we have to do one more thing, and that is something called yes, divergence. But then we're going to compute deviance. Okay, I never figured out what people really want to do there. Anyways, this is going to be a file that will be available to you. You already have this on the website. Made some further changes, and those will be posted as well. But here's the RMD file for any number of things, and here is a measure that we're going to use. But I don't think looks too odd. The target is could be Q, and that's a distribution, and you can see log, but we're looking at it relative to something called P, the distribution P, which has a lot of different points to it. This is a probability, posterior probability, and it's a little bit like log odds. It's both of these together. But look at the P times the log of the P's will give away that this is Shannon uncertainty, okay, information entropy involved. And this is called the KL divergence, which is the foundation for all machine learning at this point. Everything is a subset of this. It's an information theoretic world now. And we're using this, and I just want to do a couple of calculations with it to get us comfortable with it. Suppose we create a little tibble here. Observational model gives us these two for event 1 and event 2. Probabilities adding up to 1, 3, and 7. Then in Q, a different one, 40, 60. This might be our theoretical idea of what the probability should be. And we want to use one to describe the other. So we just have two here. And the mutate, of course, does a calculation for us called DKL. And it's basically just doing a very simple piece of arithmetic. Okay, here's the first part of this equation. Okay, I equals 1. We're going to go I equals 1 to I equals 2. So here's I equals 1, probability, log P minus log Q, all on the first one. And the second one, P2, log P2, log 2. Okay, now you know here that P1 and P2 add up to 1, so P2 can be expressed as 1 minus P1, right? Okay, and the same with Q. If we call Q1 equals Q, Q2 is equal to 1 minus Q. We could put those in here if we want. Those are deck chairs, as I say. And here we go. And here's the experiment. Okay, I don't think I needed to do that, so I had a different idea in mind when I did this. And there we go, that's good. No, here we go. We don't even need this. All right, fine. We have different arrangements, yes. So, we could do this. Let me put this in here. You're not laughing now, I can tell. That's all right. There we go. Suppose we had this 60, 40. I mean, that's a different arrangement, right? So we could play with that, or we could play with this. Okay, you can see that one has a different kind of structure as the other. But it's going to be the way P2 interacts with Q2 in each case. So P2 is going to interact with 40% here. Here it's going to interact with 60%. That's why it's different in the KL. That's what they discovered around about 1951. Kind of interesting. Okay. And here we're going to do a little picture of all of this. We're going to say, let's have our original 70-30 split, P1 and P2. And now let's move vibrate Q from a very small number to a very close to 0 to very close to 1. Remember what happens if you set these to 0 and 1, you get something called nans, or not a number. And I'm going all through this because this is good R exercise. We're generating an idea here. And Q2 is going to be allowed to go from near 0 to near 1 by units of 100. And we're going to define Q2 as 1 minus Q1. Okay, that's a new variable, so we have a mutate, create a new variable, mutate. Kind of interesting, I guess there are biological in mind here. And use the divergence to KL Kullback-Leibler. I'm always told it's Leibler. No, it's Leibler. And find the min of that and the min Q that is associated. This is like an index function. It is an index, actually. And minimum label, make a label with a concatenate. Okay, so we did all of that. Okay, fine. AES sets up the canvas, and now we populate it with geometric objects, points, lines, points, text, labels up and down and all around, and you can play with that as well. And let's see what that gives us. Let me run that chunk for us. Again, it's always good to do this sort of thing because otherwise you got to map stuff. You got to visualize it. Here we go. The minimum is right here at Q1 equals 0.7. And the minimum is, okay, it goes to a 0. That is the minimum. And it's a bathtub. It goes down and comes back up. Okay, that's the shape of this metric. Think about what this means. I mean, it's pretty steady here, downward path down to here, and it drops up, comes down. Okay, so this doesn't do much here. Not much movement in the divergence down here. So just think about that for a second. And yeah, the test today is WAIC stands for what? Wide Area Information Criterion, right? Or Watanabe. That's Watanabe Sumio. IKEK, okay, person who first got this idea up and going, coming off a commuter rail in Tokyo, I believe. Okay, and we've already put all this together. The log posterior predictive density I said log predictive probability density. Oh, wow, I don't know my stuff, do I? So LPPD, there we go, and there's a penalty. And we did all of this in longhand. So here it is in all its glory. The -2 comes up for whatever reason. And again and again and again. And here's another equation for LPD as well. This is a more complicated one, but it's the log of an average of likelihoods. Okay, so there we go. We got to use the likelihoods. The 1/18th, the 1, oh gosh, 1/18th, 1/12th, 1/6, I think is what it was. I can't remember now. Yes, that's what it was. Example. And this ends up being a score that we've used before. We used this with Jill and Will. Okay. So I mentioned something about ridge regression. I'm writing a note because I used to use ridge regression. Okay, fine. Now we're finally getting to where we want to be after such a hiatus. We're in the rethinking mode here. We're using Richard McElreath's modeling expertise here to do something with the Laffer curve. Okay, so we're going to get data from the Laffer curve, and then we're going to standardize it. That means find the z-scores. That takes an observation, subtracts the mean of all those observations, divides by the standard deviation of all those operations. Okay, observations, we're going to call that T, we're going to call that R. We could do this with a mutate, a Tibble, just didn't get that far yet. Now he has something called A-list instead of list, a special list in his parsing routine, which you must use, not list, you must use A-list. And here's the first equation. R, which looks, I guess, like tax revenue. What does this thing look like at all? Now, let's look at it, because, you know, it's ridiculous that we don't see what we need to see. First of all, let's do this, and then this. There's only 2 items in a tax rate from a 0 of 30 to 35%, and negative, I don't know what that means. And this is by country. We don't have the countries. That's all right. And look up who Laffer is. Backward bending supply curves and all sorts of other things. An economist in the Reagan and Reaganomics in the 80s, when I had to pay 15.875% interest rate on a mortgage to shelter our family. Yes, lovely. Let's put this up here because it'll be a little bit easier to deal with. And let's pop these down here. We're going to look at T and R. Now, I think I want to look at the original tax rate. So we have D, and we're going to pipe that, the pipe, into ggplot. AES, ES helps to spell that. The x-axis will be tax. Equals tax. Typically it comes right up, but today, tax rate. And yes, y will be equal to tax revenue. Add to that just a bunch of geom points. Color equals bleh. I love what they do now, that we can see the colors, the grayscale. 30% gray means very dark. Okay, that's the idea there. And we learned how to use something else. 2D, density 2D. There we go. And we'll paint that. I don't know if this is going to work, but I can't remember. Red. And let's see if we can get something to come out of this. Well, I probably needed to load in this session tidyverse. Oh, there it goes. Oh, it's points. There we go. Spelling matters, right? Back in second grade. And it did not like something at all. What didn't it like? Tax rate not found. And I believe Laffer does have it. So we're going to go through this because this is what we all go through, isn't it? Tax rates there, D. And that has tax rate as well as tax revenue. So if we start up here, that should be piping into that now. There it goes. I just didn't do it. There we go. And so this is the first thing it makes sense to do. Title it, do all these other things. And you see there's a large concentration over here with what I would otherwise call outliers. Things that are on the edge. In the deep water, these are on the shoals. This is in the mountains, on the beach, and so on. Okay, contours, very helpful to understand where your data is and what you can seem to expect. And he drew a line. This guy literally drew a line like this, back flipping through this data. That was his line. Drew it. Now we're going to look at a slightly different way to approach this. And let's make a new chunk over here. And what I want to do is eventually run this. I also want to put a summary in here. The posterior thing. Okay, we're going to run quap, which is, again, quadratic approximation. And our model is somehow R is going to be drawn from a distribution with a mean equal to intercept and slope dependent upon T. T is tax rate. Okay, so we got the other thing wrong. It's tax revenue versus tax rate. Well, we could run both models. Let's see which one works better. That'll be an interesting exercise. And we're going to draw, that's the mean, and the standard deviation or the sigma of the normal distribution that we're going to draw R from is going to be given by the distribution of exponential with parameter, lambda parameter of 1. And A is going to be drawn from this very simple normal distribution. And we're going to use the notion of regularization. Regularization is rather interesting. It tightens up our estimates. And our GPTs do it every day. Okay, so if you're doing it, So should we? Yes, exactly. And data will be equal to D. We'll look at the parameter estimates, and then we'll sample from all of this, and we'll get a look at that sample in a moment. So we're going to run a regression. This isn't the one your grandmother taught you, or grandfather, or uncle, or anybody else. Okay. Can't find R. Well, that's because I didn't do this. There we go. And this is all about variation. There, we got it. Standard deviation of 13. Mean is, for all intents and purposes, 0. And we can see that over here on the probability interval. So no longer confidence intervals. There's no confidence there. Just pure probabilities, nothing up our sleeves. You can see it's nicely centered at 0, apparently. And B, on the other hand, somewhere between a low of 0.2, 5.5% of the time, and 94% of the time we can find from 0 to 55. It's positive. It's definitely somewhere in here, 29, right in the middle. Figure that out. It probably is dead center. And sigma, which is the risk of being off by anything here, also has a standard deviation. It's an estimate, remember. And it too seems to be meaningfully between 73 and 111. Okay. Remember, these are z-scores. Z-scores are always between 0 and 1. Yeah, I don't know where that sigma's coming from. It's because it can just with this sigma here, it can just sample its heart out. Now, on the other hand, we have a traditional regression down here. And this is ordinary least squares. That's what OLS stands for. We have two models. Model 1, M. Okay, we have M. We're just going to leave M because M is the right way to do these things now, according to me, according to a lot of people like me. And you see these stars down here. We're going to call that stargazing. You can ask your various friends about what these things really mean. I'm not using these R squared. I'm not using that. I'm not using p-values. I gave those up many years ago because my clients didn't use them. And I said, well, I never liked them either. I didn't like them on my, I had to put them on my dissertation and in my articles, but I liked information criteria because even if I know the range, for example, of potential intercepts, they go from minus 0.21 all the way up to 0.21. Even though it's in 0, I'm interested in the range because it's about information. These are posterior distributions that I'm looking at, in this case, marginal distributions. Here I lose all of that. I can probably pick it up with something called bootstrapping. Okay, they're coming up with almost exactly the same numbers. What did we come up with up here? 32 is what they're coming up, 3.2. I'm coming up with 2.9. Hey, close enough for me. Okay. They're going to say theirs is exact. Actually, they're not. Everything's an approximation in this computer. Everything. It's doing an inversion of a very small matrix, but that too is going to be subject to approximation rules. Now, the supply, look that up. It's a very good tool to know. There's another one in tidyverse, I think it's out of the per URR package. It's called map, something similar. We're going to take 1,000 samples. We're going to create this simulation. Look how we create it. It's not that hard to do. Create a little function, define mu as post AS, post BS. B. Now, S is S is right here. That's where S comes in. 1 to n samples. So it's going to do 1,000 times. It's going to do a calculation. And it's going to pull AS. Now, if we look at post, once again, here's what post gave us. It gives us a min and a max of AM and BM and sigma. Now, where's AM and BM? Always go back here and check this out. I don't know where those are. I don't see any AM or BM. Okay. I call this AR. Obviously, this did something before. There we go. And that's because I need to specify this and this. Try it again. Yep, same thing. And then we extract samples from M. There we go. And now we look at the post. AR, BR, and sigma. Probably should put sigma R for revenue. Okay, just to be so that nobody gets confused later on with anything. God forbid. Yes. Well, let God give us strength at this point. Oh, no, 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 no. It doesn't like this. Non-finite difference value. Oh, my gosh. Should have left well enough alone. Oh, no. So we do have to do some changes here. But we're going to keep our original thing because I just don't want to deal with this right now. You can put initial values in here. And that is why I showed you, I'm glad actually this happened. That's why I showed you the initial values are critical to running this algorithm. And when we did level up bosses approach, which is what this is before, we did not run into this problem and should have a couple of times. But we can again play with this until all sorts of things happen. This might work. I'm just gonna play. There, that did work. Oh, and there we go. We get the same numbers. Here's what I did. I tightened this one up. I didn't know, so I tightened it up. Maybe it gave me a better starting value because it's going to sample from this distribution, pop it into here, sample from this distribution, pop it here, calculate that, put that here, sample from this distribution, pop it here, sample R, and do this a bunch of times. Okay, that's the idea. And then pick the best one. Okay. And ARBR and sigma. Okay, I left that little R off. But one more thing. Let's do a head of what this post looks like. And it's very simple. 1 to however many. And you get simulated values of these numbers throughout. And it's extracting it such that it's choosing these relative to some posterior. Okay, so it's all about parameters. These are parameters only. And we have the OLS regression. Now we go back to this and see if we can run this. 1,000 samples. And we do a little calculation and apply. So this is like a great, very fast for loop. And I have 1 to 29 of what, well, let's look at what this looks like. What does log prob look like? Log of probabilities, right? See how it's running it? It's literally a matrix. That's all. And you got to know what's in each one of these. It's got 11 by 1,000. The question is 11 what by 1,000? Now, we're going to use that matrix down here to kind of pull together what is called LPPD. Remember that, posterior predictive density. And if you look at these, this is just running R. It's basically running R. Okay. Relative to mu and sigma. That's all it's doing. It's sampling R. And it's doing it 1,000 times. It's sampling, now how many R's are there actually, do you remember? Twenty-nine R's. For each one of these, it's giving me a new sample. That's the idea behind it. For each and every one of those R's. Imagine this could be a very large matrix. Very, very large. Each observation in each row. Okay. A whole bunch of these. And with all of that, now we can do this computation. Let's look at the computation. The number of rows is the number of observations. Is that correct? Check it out. It says 1 to 29. 1 to 29. So those are the rows. The number of columns of post is just 3, remember. And log probability is 1,000 columns. Okay, so just keep all of that in the back of your head, or write it down. That's what I usually do. So we're doing another S-apply, another big for loop across 29 observations. For each observation, we're going to calculate the 1,000 log probabilities. Okay, so that's I is each observation across all columns. Well, that's why I did 1,000 columns minus, we calculated this already. And this is a log sum exponent, very quick algorithm for doing that. You take the exponent of the probabilities, okay, and sum those up, and then take the logarithm of the whole thing. And subtract this. This is, remember, you're taking a logarithm, it's like dividing by n samples. It's 1,000 samples. We come up with minus 38. 38 bits left on the table. That's another way of putting it. Okay. This is what we'll use. This sum will be used inside of the WAIC formula, WAIC. And this one here is very simple. This is just the variance of that great big long row. Okay, 1,000 of those. We only had one. And this will give us summary of it because it's going to be across the mean of 2, max of 4.7, and so on. That's what it was calculating through this. You sum them up, and we get the number we need, 6. These are log probability units, so these are in bits. Then here's our weight number. Very straightforward. Standard error is another one we can calculate. We have a vector of all of these. Let's look at this vector. $29, right? We have 29 numbers for the WAIC. Okay, 29 of them. Wonderful, because now we have a point-wise way of putting this on a graph. Okay, that's the idea. And that's for each of the points, each of the 29 observations. Square root of this, that's 23. Number of observations times var. So that's the story there. And the rest of the story is about, well, playing with this a little bit. There we go. We can get all these LPPD numbers for each of the observations. We only had 3. They're all negative because log of a number between 0 and 1 is always going to be negative. The penalty is computed, and we also have standard errors, which is going to be the same for each. Okay, that's 29 by 4 items. WAIC, LPPD, penalty, and so on. So we're almost there. It's kind of interesting. And I have another model in mind using the student t distribution. Call it M sub t. We could run that. Now it gives you, allows you to sample further out into the tail of your observation. That's what this is going to allow us to do. And if you use a very small, what is called degrees of freedom, a student was an actual person, worked at, oh, Guinness is good for you in Dublin. Looking at plots of fertile hop producing land, right? Anything for beer, yes. Here's the same model. Ooh, that one did work. And notice we're getting, oh my gosh, because we sampled out further, the intercept is all of a sudden interesting to us. Doesn't cross 0. Some of the information from B dipped into A. That's how I read this range. Now it crosses 0 just a tad, dipping into A. And this number here is still pretty tight enough for me right now. Okay, so we have a very different model. And the question is going to be, well, how much information does it have? 75 minus 33. Okay, what was the other one? We can do it like this. Or we can do something called compare. Now it's 95. So, you know, this is going to win. There we go. It's leaving less on the table. So here, oh, you got a compare function. Which has given us everything we need. Standard deviation, because it was all done with the posterior simulation of 1,000 times each and every observation. And we see that, again, the comparison is in favor of this other distribution called student t. Well, the difference between it and itself, okay, it's going to compute 74 versus 90, 16 bits there. ESE, I don't have to worry about that right now. But this is interesting. Like this uses less penalty than M has. Less of a penalty, less of a variability of the LPPD, or what drives the LPPD, which is the log likelihood. So less variability there. But it also tells me something else about this. The student's t distribution is a mixture distribution. It's a mixture of the normal with the chi-squared or chi-squared distribution. And because it's that, yeah, there's a lot of other dynamics involved and probably some singularities. We're not going to worry about that. So the more complex the model, we just made our model more complex. We actually added another variable called degree of freedom and a different distribution. So yeah, so this goodness of fit is going to favor T. The right measure, but it leads to more complex models. It's like everything else, like R squared and everything else. Use of multiple criteria will complement regularizing. Right, okay, fine, all of these. Model selection, we're going to do one more, and this is the last thing we'll do today and for week 4. So we have WAIC 1 is the initial model, normal distribution. And we have the student T, which is 2. We're going to take a difference between 1 and 2. So, right, remember 1 was bigger than 2. Okay, so remember that. So it's the excess of information lost by 1. Taxes, model comparison. Yes, that all works. Make a plot. Let's make this B here. Now watch this. So this is just very similar. Here's the tax rate, and here's the difference between the two. So it's going pointwise now. It's a different plot than what I showed you with PSIS. So 10 units, 12, 13, 15, 16, 17 units more than the normal distribution model is over the student T model. So it's leaving an awful lot on the table. Absolutely, it's a tail. It's tax ID number 1, 12. Yeah, all the rest are around here, which is what you like, very little difference. But we have one that's clearly an outlier, deserves investigation. Lots of investigation. Okay. The tax rate here is how many standard deviations from the mean. Notice it's got a tail down here and a lot of stuff. It's always greater than the mean up here. Those are z-scores. So we'll look into that. There are trade-offs. Think about the trade-offs here. The big one here is over and underfitting. And our model with PSIS will help us out there. And we'll do that with stargazing with Cassiopeia and Cepheus in week 5. And layer onto this another piece of our analysis, which I hope, I already know it will, I hope will excite you a little bit with wolves and moose, those two customer bases. The interaction model we need to get back to, but we have all the tools for the next 3 weeks to play with interaction models, including things like how can you confound your models? We do that every day. How can we straighten out some of the issues associated with the models? The covariability of so much covariability built into our ordinary differential equation model from system dynamics that it just begs for an answer. An answer is going to come at a intellectual and programming cost, but it will be worth it. And I will bear that burden, and you will help me with that as we go through that. But the Cassiopeia effect, read this. It's a very interesting thing. I'm going to render this and say we have done enough work for one day. Play with this. Just play with it. And I'm going to leave you with that note. And let's see if they'll let me do that. Anyways, thank you very much for your kind opinions and thoughts as we go forward, and your attention. Most importantly, your attention. Encourage each other daily while it is still today. So much more to do. So many more interesting things. There, look at penalty. There we go. Uh, Things that we can play with and should play with. And oh my goodness, look at this. We're going to have a gift at the end of this. Oh, yes, we are. Oh, no, we're not going to do that. No, I'm going to take that out of there. Oh, yes, look at this. Oh, these are going to be great diagrams to play with. And this will be what we did before. Pareto K. Reliability versus predictability is what this will show us. And this model is interesting because it gets water out of the Flintstone in the wilderness. It's really very good. Pulling it apart with a complete study. This is where we want to get to. These are the diagrams we want to see and need to see in order to do our analyses from here on out. Okay. So we will do that. Thank you very much, and see you in the next round. Take care.